There's a
Hello, ladies and gentlemen. This is Alex Handy, Senior Editor of the Software Development Times, welcoming you to this webinar from Aerospike entitled Databases and Containers from Development to Deployment. I'd like to thank you all for attending, and I'd like to introduce now Alvin Richards. Alvin Richards is the Vice President of Product at Aerospike. In his previous lives, he served as the engineering lead for commercial products at Docker and technical director at MongoDB. In more ancient history, Alvin held various engineering leadership roles at SaaS credit card processing company called Beam, database and storage integration company NetApp. I think we all know NetApp. Database archiving company Outer Bay, and database data warehousing at Oracle, another company we all know very well. In addition to a bachelor's in computer science from the University of West London, Alvin also earned a bachelor's in photography from Nottingham Trent University, and hopefully he will be able to give us a nice clear picture of databases and containers and how they can work together. So I will now hand it over to Alvin.
Thank you so much for that introduction, and good morning, good afternoon, good evening to everybody who's listening in. What we're going to do today is try and set the scene of why containers, why you need a scalable database, and how you plumb these things together. So I'm going to do a couple of introductory slides, and then I'm going to pull open a terminal console and then pull up an editor, and we're actually going to bash away at some code. As always with live demos, I have prayed to the demo gods beforehand, but as with all live demos, it could all go horribly wrong, and you can see me mistype many times on the command prompt. So it should be some fun. Really, I kind of want to talk you through code examples of how you actually make this work, rather than just keep it some sort of static presentation and a bunch of slides. You're all developers. You all want to know how this thing really works. You don't want to see some glossy marketing slides. So on that note, let's start off with some glossy marketing slides. So let's start with the conclusion. Containers and databases, essentially you get happy developers. They have a very easy way to go develop on their laptop or their desktop and try out various configurations and deployments. They can test it all, everything's great. But if you think of containers as these ephemeral devices, and you think of ephemeral and databases, then you have a whole bunch of DevOps headaches. How do I ensure that these containers, whilst they have core data that I value, how do I ensure that that data is reliable and is redundant in multiple places? How do I form these database clusters, and how do they self-heal as those containers come and go? And how does my database tier find out about this ephemeral database that's ever changing? So these are kind of key things that we kind of want to talk through today about how you make containers and databases play together nicely. I think the context for this whole kind of discussion is, we've got an existing set of architecture. Right at the bottom, we've got our databases. They could be relational, it could be mainframe. You might have some transactional systems. Out on the left-hand side, you've got some analytical processing, and then you've got operational databases, typically with a cache in front, running your real-time applications. And the kind of cost and complexity and the maintenance of that cost equation just doesn't work very well, especially when you consider things like scalability. You suddenly want to jump 10x the amount of traffic through your website because you've now launched a mobile application. How do you actually deal with that in a realistic way? So kind of the fundamental things is people are looking at new architectures because what they've been using the last 10, 15 years is running out of steam or is no longer cost effective. The second problem is the existing deployment models are kind of broken too. I've got my developer, he develops some stuff, maybe he checks it into GitHub or his favorite source code control system. We've now got to push that out onto test. Well, the test environment's probably going to look pretty different to the development environment. I go from test into production, and perhaps I've got Ansible or Salt or Puppet or Chef, and I'm trying to keep these environments the same. they're never going to be the same or identical, which gives the developer the challenge of how do I debug something that fails in production that never actually fails in my test environment, because my test environment doesn't look like at all my production environment from the dependencies or the OS versions and so on and so forth. So the way we kind of deploy things is kind of pretty broken too. And then you look at our infrastructure, and if you look at a sort of traditional database system, you're sitting on top of an operating system, so there's an operating file system, then you've got a page cache, and then you've got a block device in order to actually get to the thing you can do a read or a write against. And you've got all of these layers of indirection. You put virtualization in there. Now you virtualize all these pieces, and that actually doesn't allow you to get anywhere near utilization. So you want something more like on the right-hand side where your database is interacting directly with memory, and then you can massively parallelize those reads and writes directly to the block interface, so you can take the best advantage of the SSDs or the other storage behind that. So fundamentally, you need to have a different application architecture, different deployment architecture, and you want to really utilize different types of infrastructure that are now available. So we're going to try and meet some of those challenges using containers and the way that we use databases. So that's kind of what we're going to spend our time on. So briefly, let's talk about containers. I'm sure you've all heard about them. Some of them you may be actually using them already. You may be actually having them in production at the moment. What is the mission of containers? Well, essentially it's to reduce complexity. It's to be able to go from the build all the way through the run to ensure that you've got the same set of code, the same set of dependencies all through that life cycle. And in terms of the kind of container stack, at the bottom you've got a set of open standards, and we'll talk about that in a minute. You've then got the plumbing, essentially to run and execute those containers, and then you've got the platform, which allows you to do clustering and distribution to distribute your workload across all of those execution environments. So kind of broadly, that's what the container landscape looks like. So what do containers give you? Well, essentially encapsulation dependencies. You can specify which version of Python you want to use, for example, which OS packages you want to install. You can put your code and your code dependencies within that container. And so that gives you a nice envelope to stuff all these things in, and then you can pass that envelope from team to team or developer to developer, and they've got exactly the same bits, irregardless of where that's deployed. Second thing that containers gives you is process isolation. If you think about how virtualization has been used, essentially it's been used to get better utilization out of big hardware. You can run multiple applications and ensure that they don't interfere with each other because you can put policies around the virtual machines. Ultimately, what you're really doing is creating process isolation of the thing that's running inside the virtual machine, but the virtual machine is giving you all of this kind of baggage for the virtualization of the I/O and the network and all this other stuff, when all you really need in order to run these applications on the same physical hardware is process isolation. So one way to think about containers is faster, lightweight virtualization. And that's an oversimplification, but just so that it helps to give you the context of why. So here's a quick example of what a Docker file looks like, and we're going to be using Docker as our example for our container definition and orchestration. So you can see here in this Docker file, we first described that we're going to use a particular language, Python in this case, and we're going to use a particular version, which is 2.7. We next then add in our source code, and you can now see a series of steps when we ensure that we're getting all the right packages installed on that image, so that we've got Python dev and SSL dev and so on and so forth. We can do regular commands. You can see the next step is to install our Python dependencies. So you can quickly see how you can aggregate all of the dependencies, your code, and everything else you need to execute your application code within this definition. In terms of the Open Container Initiative, as you can see, there is an army of organizations and companies out there who are helping to go define the image standards and other specifications so that you essentially don't have vendor lock-in of your images. And so clearly Docker is one of the leading lights here, but along with the organizations like CoreOS and Pivotal, they're all working to ensure that those image standards are interoperable so that you're not locked into a particular type of vendor. Just to kind of try and illustrate the Docker ecosystem in pictures, on our top left you can see we've got a container. So as I said, that encapsulates your code and your dependencies. And moving into the center, your containers are run by a Docker engine, and that's Mollydoc the whale, and it's the thing for executing all of those containers. How do you get a Docker engine? Well, you use Docker machine on the bottom left to go provision those engines. You can go and provision as many as you need. Typically on a laptop, you're going to have one engine running, but in your test environment, you could literally have tens or hundreds. And so how do I now orchestrate all of those containers? My application or my microservice may be built up of a number of disparate components. Well, this is where Docker Compose comes in. Docker Compose, as we'll see later, is the way to describe these set of services and orchestrate their deployment and execution together. And Docker Compose can orchestrate against a single engine, or as you see on the top right, it can actually orchestrate against a swarm of engines. And so Docker Swarm is Docker's clustering mechanism for Docker engines. So you can spread these engines across many physical hosts and then deploy your application to that cluster. So hopefully that will give you some idea of some of the components we're going to talk about today and how they fit together. Okay, so that was the kind of container part. Let's quickly talk about Aerospike. I have to do some shameless marketing plugs at this point. And I'm going to tell you a little bit about Aerospike and why we think Aerospike is actually a really interesting and unusual NoSQL solution. And then we'll talk about how this fits into the containerization of databases as we go forward. So the kind of bottom line, Aerospike is a key value store. It's highly scalable, and this is an illustration against an alternative database where we can typically show 10x reduction in cost associated with a certain workload. Typically, we would see out of a single Aerospike node being able to do 1 to 2 million transactions a second. And so it's designed to be high performance, low latency, and highly scalable. How do we do that? Underneath, essentially, we're a big hash partitioning scheme. We use RipeMD as the partitioning mechanism. We have a redback tree as the primary index. But essentially, the scaling mechanisms are there to ensure that you can dynamically add and remove nodes, and the data gets rebalanced across those nodes, and we can essentially auto-heal. So Aerospike's got some natural abilities to actually deal with modern compute deployments, whether that's virtualized or, as we'll see, containerized. How do we do the speed? Essentially, we're optimized for flash. We have a log-structured file system, and what we do is ensure we do big writes. We don't do a copy on write because that causes the flash wear problems that you're probably very familiar with. We do a log-structured mechanism to ensure that not only can we get the throughput we need, we can ensure that the latency response over time remains consistent. And on the right-hand side, you can see some typical benchmarks. This is YCSB to show the kind of throughput and the latency you can get from an Aerospike cluster. Okay, I think that's almost the end of the one kind of use case. So just talking a little bit about use cases. Obviously, we're used where you need high throughput or low latency or both. And so this is a sort of real-time fraud prevention where Essentially, Aerospike is used as the system of engagement or the database at the edge, and that's used for processing ever more complex set of rules in order to ascertain whether you want to deny or accept the transaction request when somebody swipes a card. You can imagine rules are getting more and more complex. There's much more data. So, for example, you need to make the decision when somebody swipes a credit card at Heathrow Airport, the fact that they 12 hours before swiped their credit card in San Francisco Airport and brought a plane ticket 2 months ago for this flight. If you have access to that data in real time, then you can actually make better decisions. So typically we would see a kind of solution like this paired up with your historical data lake, where you're doing Hadoop or Spark processing to execute your models or your machine learning, and that gets fed back into Aerospike so that those models can be compared with the data that you're receiving in real time in order to be able to process the request and make the decision. All right, so enough of marketing. Database and containers. How do they really work? What do you really care about? And this is the crux of what we're meeting today about. So I kind of think the requirements are like this. What do you care about is data redundancy. You need more than one. If a container is ephemeral and it disappears and arrives, you need more than one copy of the data. You need to be able to, if you've got a distributed database system, you need to be able to form that cluster automatically. You don't want to have somebody typing away at a console, doing manual commands in order to reform the cluster each time the containers appear and disappear. You need to be able to deal with loss of nodes and do the self-healing and the repairs needed. But also from your application tier, you don't want to be reconfiguring the application tier in order to talk to the ever-changing cluster underneath. So those are the kind of key requirements. And if I was to compare Aerospike in this list, how does that meet those set of requirements? Well, in Aerospike, we automatically replicate data. So data replication built in is a key requirement in order to look at these types of architectures. You need the ability to reform those clusters, rebalance, and also ensure that your application can still connect. So built into our language bindings for Java and C# and Python and all the other popular languages, our client automatically rediscovers the shape and the topology of that cluster. So as that cluster changes, the application can rediscover that. That means you don't have to write any code, irregardless of what size that cluster looks like or where it's deployed. As we talked about earlier, we're rebalancing, so we can automatically partition that data across the available nodes, ensure that there's multiple copies, and if you lose one of those copies, we'll ensure that an additional copy is made to meet those requirements. Okay, so let's talk about a demo. So the idea is to get from development through to deployment or to production. So we're going to build and run an application in development. I'll do that on my laptop, and then we're going to deploy to a Docker Swarm cluster. And so we're going to take our application from a single web node and a single database node. We're going to put the application behind HA Proxy so that we can scale out the web tier, and then we're going to then scale out the database tier. So ultimately, we're going to kind of start like this diagram where we've got a web and web container, and we've got an Aerospike container, and we're going to end up with a production deployment that looks something like this diagram. So that's the goal for the next kind of 15-20 minutes as I bash through code. So let's do the first part of this, let's go build an application. So if I go and pull up my editor, okay, that's good, that's refreshed. So I've got a very simple Flask application. It's a Python application. It's really not complicated, and the idea is we're not really building an application here, but we're doing a piece of code that's going to do some interaction with the database. So we can actually see some key pieces in this piece of Python code. You can see that we go and establish a connection to the cluster. And as we said earlier, Aerospike is key value store. So you'll see things like a put here, where we're actually writing a key value. We're going to do some increment operations, as you can see in the following two statements. And then we're going to do a query through a get call in order to display some results. So that's the kind of Python code. It's very simple. It's not meant to be production ready at all. You know, I can't write Python code to save my life, as you can tell in this example, but it's to give you some flavor of what you would do. So let's go and run this application. So I'm going to use Docker Compose because I'm using Docker Compose to describe my various services and orchestrate those. And so I'm going to do Docker Compose up, and that's going to start my web and my Aerospike containers. Okay, so looks like they're up and running. So let me go to my web browser, and we'll see the results of my most amazing application. And as you can see, what we have built is a web counter. We think this is going to be completely change the way people think about web applications. I'm talking slightly tongue-in-cheek, but as you can see, I can refresh this page and I can count the number of hits. And so we've got a very, very simple application. Now, if we now look at some of the Docker files and the components behind that, let's take a quick look. So as we saw earlier, here is our Docker file, and this is describing the Python application. We saw this example earlier, but you can see we're using a particular version of Python. We're ensuring some packages are getting installed on our Linux image. We're installing a set of Python dependencies that we need, and then we go and run our application. Okay, so you can see here it's a very simple encapsulation of all the things we need to run our application. And the great news is now that we've encapsulated that, my friend Jim, the developer, who's 2 desks over from me, can take this Docker file definition, and he's going to be running it in the same way. And when we now give it to Jane, who is our DevOps person, she can take the same definition, and now the application is running identically across all of those different environments. So that's the kind of definition of our application. Now let's go and look at the compose file. So Docker Compose is simply a mechanism to orchestrate these various services. So we've got 2 services here. We've got the web service and we've got the Aerospike service. So let's kind of talk about the web service first. The first thing you see here is a build command, and that simply says how you go about building the image that represents the web application. We expose a port, so exposing port 5000, and we're saying we're going to link to the service called Aerospike. And so this will establish that the fact that these 2 containers can now communicate with each other. We're going to define a host name, and we're going to set a couple of environment variables. So if we look at the second service, Aerospike, instead of building the Aerospike image, what I'm going to do is I'm going to download one of the published images that's stored up on Docker Hub. And Docker Hub is Docker's service for publishing and storing images. So we're going to use an image from Aerospike, and it's Aerospike server, and we're just going to use the latest. Right? I'm a developer. I always want to use the latest and greatest. I don't want to tie us down to a particular version, so I'm just going to pull out the latest. And so this allows us to actually define all of the various components that make up our service. And you can imagine very easily that once you start building microservices, you've now got a way to describe all those constituent parts that you want to deploy as a single unit. So that's the very simple stage of how do I get something up and running as a developer. So that's the first part. We've built an application and everything looks good. and we kind of talked about the Docker compose file and the Dakka file, so we won't cover that again. Now I've had it running in development, you know, the development team's given it the thumbs up. We now want to deploy this into production. Clearly, in production, you don't want to run a single web node and a single database node. We think we're going to have a huge number of hits, a huge number of traffic, so let's kind of design our deployment so that we can utilize the work that was done in development, but then basically inject the behaviors that we need in order to be able to create a scalable application. So essentially what we want to do is we'll start off with a single node behind HA Proxy, and then we'll scale up our web tier to go and add more web nodes in order to be able to deal with the incoming traffic. Now, we need to kind of at this stage talk about networking in Docker. So this kind of picture's a little busy, but hopefully you'll get the idea. So in this particular example, we're going to be running 4 Docker engines. And as you can see, they're labeled Swarm 0 through Swarm 3. And inside each one of those Docker engines, we're going to have various containers running. We're going to have, as you can see on the bottom layer, we're going to have a number of containers that are running Aerospike ultimately, a number of containers that are be running the web containers, as well as our HA proxy. Now, in Docker, there is obviously, you can do the equivalent of NAT translation. So each one of those Docker engines ultimately has an IP address, and then the ports exposed means you can directly connect. What we're going to use in this particular demo is a new feature in Docker called multi-host networking. We know that we don't want to run all of our web and our database tier on a single host. We want to spread those across many physical hosts. And so Docker has introduced something called multi-host networking and a particular driver called the overlay driver that essentially creates a VXLAN underneath the covers, and then those containers will then join that VXLAN. This means that each one of those containers now has essentially a unique host name and IP address. And so you can now deal in a very simple way adding additional nodes in, because you are not, each container has a separate IP address, and therefore you don't have to do mangling of port numbers because multiple processes are running on the same host. So we'll be utilizing this new networking in the next part of the demo. So let's kind of scale up the web tier. So let's go back to my console. So I'm going to be now, this is my production deployment, and so I can do a Docker, if I type correctly, I can do a Docker PS and nothing's running. So again, I'm going to do a Docker compose up to bring up all these services. I'm going to add the -d flag, which will just essentially put all of this into the background and give me control of the console. So you can now see that we've got 4 services up and running. If we go back to our web page, we can now go and do a page refresh, and our production cluster, well, we've now got 1 hit. So this is great. We can now actually see multiple hits on our new production cluster. Now, I've got a little application you can see below, which is giving us a visualization of our Swarm cluster. So you can currently see that there are 3 Docker engines running. And as you can see in Swarm 2, this is where our web app's running. In Swarm 3 is where our Aerospike node is. And in Swarm 0, we've got our 2 discovery services, one for HA Proxy and one for Aerospike. And we'll talk about those in a second. So I've got 1 node up. Now, I now want to start additional nodes. So I can use a great facility in Docker Compose called Scale. I can say the service name, which is web, and I can say I want to have a total of 4 containers running. And so what Docker Compose will now do is it'll figure out there was only one running, and it starts an additional 3 services. So if we go back to our visualization, you can see down here we've got our additional web nodes being added. And if I go back to do a page refresh, you'll see that we can take advantage of those additional web nodes, and our application carries on running without having to do any recoding. So that's pretty cool. What we can also do is, why don't we peek inside the database to go look at the data that's recorded. What I've done is I have put Aerospike's command line utility AQL into a Docker image. So I can now simply just run that Docker image. So Aerospike tools, AQL, and all I have to do is give it a host name, which is prod Aerospike 1. And I always get this wrong, excuse me. I have to put a run in front of there, and I also need to say which network I'm on. Okay, so I can do, select star from test.hits, and you can see each one of those hits is being recorded in the database. And I've also got a summary table. And as you can see in the summary table, we're recording each web node and how many hits that specific web node has got. So you can see that the HA proxy is now helping us out. It's routing those requests in a round-robin fashion between those nodes. And you can see the total number of hits and the number of hits per node. So that's already great. Now, what I did forget to do, we talked about Docker networking, that we have multiple networks. We have our internal prod network, and we've got our external network. And what I do need to do before I carry on is I need to add my discovery nodes to both networks. So let me just quickly do that. If you give me a second, network connect to the prod network, I need to do prod HA proxy 1, and then I need to do prod discovery, and I'll explain what I'm doing in a second. Okay, so if we go back to our slides, we've talked to, we should actually look at the code. I know, I realize I put a slide in there to remind me. So how did I do all of this? So I have got a Docker Compose file to orchestrate our production service. So what we have here is a service that describes HA proxy, and I'm using a syntax in Docker Compose where you can extend an existing definition. So this is great as you go through the life cycle, because what it allows you to do is inject additional behavior from those files that the dev team gave you. You can inject the behavior that you need for test or production. So one of the key things in Docker Compose is that you can add constraints and affinity rules. So you can see this first constraint, which is I'm saying this particular service needs to run on a particular node. Equally, I could have said it needs to run on a node with SSDs or this type of memory or these type of other services. But I'm just going to give it a simple constraint to make that easy to understand for people on the call. Now I'm looking at my web service now. So instead of building my image from scratch, I'm now going to use a posted image. So as my development team has finished, what they have done is they've posted their image to either Docker Hub or their local registry. And now when I orchestrate, I'm using that image that they posted. Again, we're going to extend from existing files. We've now got our discovery piece, and the discovery piece is essentially allowing Aerospike to automatically form clusters, and we'll see how that works in a second. Again, I can inject additional behavior like adding in a particular constraint and so on and so forth. Going down to our final fourth service, this is the Aerospike container. This is the database container. This is where the database is physically running. Again, we're extending from a base definition, but you can do something really interesting here. So if you remember from our development, we said pull the latest version of Aerospike. Well, typically when you push into production, you want to nail this down to specific versions. And so as you can see here, we want to ensure that we're using a concrete version of Aerospike, just to ensure that we know what we're running in production. Finally, down here, we have an affinity rule. So, you know, like most distributed systems, you don't want to end up running all of your containers that represent your database on a single physical host. So this affinity rule simply ensures that we only have one Aerospike container running per host. And this is kind of critical so that you can actually describe your deployment topology and the needs that you require. So this is kind of how we describe all these services for our production deployment. So if we go back to our slides, we've talked about these couple of things. So we've kind of now scaled the web tier, and everything's going great. People are loving our new application. It's counting very well. But now we've realized that we've reached the limit of capacity for a single node. So how do we now scale out the database tier? So let's do a demo of that. So as we saw earlier, I can do Docker compose, and then I can say scale Aerospike, and let's add a couple of extra nodes. So we're going to ensure that there are 3 containers or 3 nodes of Aerospike running. And as you can see, those containers start up. And if we go back to our visualization, you'll see that we now have a couple of extra database containers running. Under the covers, what's happening is Aerospike is reforming that cluster. And so it's redistributing the data around. And if I do a refresh on my web application, we'll see that without having to redeploy the application or recode the application, I am now I can now take advantage of that wider Aerospike cluster underneath. So we can quickly run another set of commands and go and look inside Aerospike to see that topology. So if I do a Docker run on the prod network, Aerospike, Spike tools. We're going to use the ASADM utility. We're going to run the info command on one. We can run this on any node, but I'll just run it on the first Aerospike node. And I always mistype. So what this is doing is it's going out to the Aerospike cluster and asking the cluster for its topology. So as this command goes and executes, you can actually see this is starting to report back. And as you can see, the number of nodes is listed, their IP addresses, and so on and so forth. So this is just a utility within Aerospike, so you can actually go and see that cluster. And this is just to show you that we have really formed a cluster of 3 nodes under the covers. And we've done that automatically without having to do any manual intervention. We didn't have to type anything. And that cluster has formed for us. So that's kind of, going and building out that cluster. So how did we do that? Well, what we have done is we've taken advantage of the Docker Event API. On the right-hand side, you can see this is an excerpt of a diagram on the Docker website where you can see there's a number of states and events and transitions that can occur internally within the life cycle of a container. So you can see right in the middle you've got running, and you can, using the docker kill command, go through this die state and so on and so forth. So there's an internal set of remote APIs that you can call to understand these critical events of containers arriving and disappearing. The second part we used is a component called Interlock, written by Evan Hazlitt, who is an awesome engineer. You can see his Git repo there. And essentially, what Evan has done is he built a framework that would listen to these events and allows you to create plugins so that you can do specific types of behavior. So one of the plugins that he provides is for HA Proxy. And so this is how we got the automatic registration of the additional web nodes. If you've ever used HA Proxy or a similar load balancer, typically what you have to do is you have to do some configuration so that the load balancer knows about the additional nodes and how to contact them, and that requires reconfiguration. Well, his HA Proxy plugin does that on demand by looking at those events, seeing whether that's a web container, whether it needs to then attach it behind HA Proxy. What Aerospike released a few months ago was our own plugin that would essentially listen for those same events and then add and remove nodes automatically from the to the Aerospike cluster. And so this is how we managed to add in those additional containers. We simply started those containers up, and they automatically self-formed into this cluster. So we're using a combination of the event APIs, Interlock, and our own plugin in order to actually make the scale up and scale down transparent to the operation side. You just need to scale using the Docker compose command, and the cluster automatically reforms. As we saw with our our client for Python, you don't have to actually do a reconnection. That's automatically dealt for you. And so as those containers come and go and the cluster changes its topology, the client is automatically discovering what that topology looks like. What does a plugin look like? As you can see here, this is a part of the Go code that's included in our plugin. But essentially what this is doing is it's running a specific command on Aerospike to inform the other nodes of existence. And you can go through and look at the GitHub repo and look to see how that works. You'll see it's a very, very simple set of commands that have to be executed. Okay, so that was the demo. That was showing with containers and a database that's got the characteristics that we care about reliability and redundancy of data, and being able to integrate with the Docker ecosystem. It means that you can get a database tier that scales horizontally or scales up simply by starting containers. And if you've got smart or intelligent clients, then your application code gets unaffected by the fact that that topology changes. But there's a couple of other things we should think about in terms of deploying databases on containers. And one of the obvious things to talk about is whether you store data within the container or whether you store it outside of the data. Remember that containers are ephemeral, so as soon as I shut down that container, if the data is within that container, then that data is gone, right? So on the diagram on the left, that kind of illustrates that. And that's kind of great because you've got an encapsulation of concerns, and for developers, this may be great. You know, they start up the container, it's got data in it. When they shut the container down, the data disappears. It's all scratch data. Clearly, this is not a smart move for production deployments, because you shut down all your containers and you lose all your data. That's probably very problematic for all of you. So there's a couple of options there. On the right-hand side, you could actually ensure that the container is writing to files or block devices on the host where the Docker engine is running. Or alternatively, if you're using something like, for example, Amazon's EC2, you could be mounting an external EBS volume in order to write that data to. So this comes down to what kind of durability do you need for your data? Is the loss of a host, if that results in the loss of your data, is that problematic? Do you want to store the data outside of the host so that I can mount that volume to a host if you need to replace the host for any particular reasons. Clearly, with a technology like Aerospike, where we've got inbuilt replication, there's going to be multiple copies of this data. And so then you're going to do some trade-offs through the complexity of your deployment, of whether you want to use external volumes or you just want to use the amounts of the data volumes on the particular host. There is a third option, and this was introduced relatively recently in Docker, that you can actually have essentially a data container. And what you can do is, as you start your, for example, your Aerospike container here on your left, you can use the volumes from switch, and essentially what that is doing is making the data inside the other named container available to this Aerospike container. And so this is a kind of third mechanism for how you encapsulate your data and where does your data get stored. Now, in these data containers, there are special rules for their destruction, because clearly if you shut down that container, you don't necessarily want to lose all the data. So there's some safety mechanisms for these types of containers where you have to go out of your way to destroy them, but it means that your data is now encapsulated in the container and you could move that container around. I would say this is still a fairly new way of thinking about persistent storage for data. From our side, we've not done any things like performance analysis of this particular topology. So I think the jury's still out on this one, but you should be aware that that's another way. Right, so we're coming up to the top of the hour. A quick summary. Essentially, Docker and containers gives you a simple way to deploy in your development, test, and production, allows you to specialize as you go through those layers, but it gives everybody an identical environment to run in. Hopefully we showed that you can scale out the various tiers of your application, whether it's the web tier or the database tier, and we've given you some inclination of how, if you make the right database choice, you ultimately get a solution that is very simple to scale and reduces the administrative burden. All right, so I think we're going to move on to some question and answers. I want to thank you for your time so far. There's a couple of quick links to where the code is for this demo, the Docker images and deployment guides, and feel free to reach out to me on email or Twitter if you've got any follow-up questions. I'm more than happy to answer that for you.
All right. Thank you very much, Alvin. Ladies and gentlemen, please feel free to submit your questions right now. We already have a few in the queue that we are going to ask, but please feel free to type them up. We have about 10 minutes for questions here. So I'll begin with the first one in the queue. Do you see containers as a viable mechanism for production operations?
I think that's a really great question. So I think it's a bit like virtualization in 2002, 2003. There's clearly some classes of containers that are very well suited for going into production, and I know people are doing this now in very large enterprises. Typically, people go with their web and application tier first, or other services like that, because there is generally perceived low risk. With the more complex services or things like persistence, I think those are going to take a bit more time to get into production, because people want to get their feet wet with the things that they know and understand how they can deploy them at scale. And the web tier is a real obvious choice for that. But there are many large organizations I've worked with who are very quickly moving all of their deployment and all of their services into a containerized environment. So it's very exciting times. I think, as always, I think you have to go into this with your eyes wide open, and you really have to thrash it in your own systems to understand the characteristics of how you manage and monitor and administer these types of deployments, because you're going to need to learn how to do this and figure out the tooling that really makes sense for you.
Okay, our next question is, can we scale up and down the tier based on system utilization? For example, when disk space is 10% availability, launch a second container.
Yeah, so that's a great question as well. Docker's orchestration component, Compose, has a number of characteristics that describe, as I would say, the kind of static environment. If you look at the other orchestration components like Kubernetes or Mesos, for example, they include additional kind of runtime behavior so that you can actually do things like when you're getting with a certain type of utilization on disk space to kind of be able to be reactive on demand. And so I think that that's achievable. You probably want to have a slightly different set of tools in order to achieve that goal, but you can do that.
All right. The next question is, what are the performance ramifications versus bare metal? Are there any benchmarks that you have to support this?
Yep, we've been working diligently to really understand what that means. Now, Aerospike is a very high-performance, low-latency database, and so we look at those characteristics very carefully. And so we're running through that internally in our labs and our internal systems so that we can, not only publish a benchmark, because that's kind of nice, because people like that. What we really care about is building the deployment guide so that people can be successful deploying in these architectures and knowing what the trade-offs are. And so we're not quite at the point of being able to publish that. That's stuff that's in progress, but we care very much about ensuring not only people can choose whatever deployment technology they want to choose, but they're successful in those environments. And that's where we want to spend our time and make sure that we personally have got our I's dotted and T's crossed. There's anecdotal information out there that you can see out on the web of various organizations from IBM all the way through to small startups who have published their own data in this space. So there's plenty of that material out there if you want to go hunt.
Just want to make a quick announcement that the slides in this recording will all be made available to everyone after this is over. That has been a question, and you will indeed get these slides and a recording of this webinar after it is over. A link will be sent to you via email. So our next question is, do you recommend running Aerospike database and Python app and a Python application with HA proxy in the same network subnet or on a separate subnet? The database subnet typically is not exposed to the external internet.
Great question. So this is kind of why we kind of constructed this sort of demo. If you remember, if we went back a couple of slides, what we've got is actually two networks. We've got our external network where we're getting the incoming HTTP traffic, and then we've got our internal prod network, which is how we mesh together the web nodes and the Aerospike database nodes. And that's essentially a private network. This is one of the reasons we ran two commands to join our HA proxy to, by default, it was connected out to the public network. We needed to run the Docker network command in order to get it to join the private network. So Docker is working pretty hard in order to actually allow you to create these networks to give you that subdivision. So, for example, you're not exposing your database nodes out to public web traffic or public IP traffic, because that would make no sense in any deployment. And that's kind of really the purpose, or one of the purposes, of the multi-host networking and the overlay driver, is to ensure that you can use your common best practices and you don't have to give up those types of things in order to deploy.
Okay, our next question. How do you run Affinity Rules to create two different containers separately and not end up on the same host?
Great question. So I'm going to go back a few slides. Bear with me. And what we can see here in this example on the screen is I'm creating an Affinity Rule. And there's two parts to this. First of all, we'll see the Affinity Rule that says com.aerospike.cluster, this is just a tag, it could be anything, is not equal to awesome counter. And that's basically saying there can't be a container with a label awesome counter. You can't deploy this container if a container is already running with that label. You can see a couple of lines above that we actually define that label. And this is how, through this simple mechanism, I can guarantee that one and only one container of this type is running on that Docker daemon or Docker host.
All right. Our next question. When using a data store outside the container, does replacing an Aerospike instance, does it not cause migration to start?
That's a great question. So let me go back to this picture over here. So Aerospike is a distributed database. As I said, think of it as a big, large hash table. And so we partition that data. And clearly, if you take out that container or that daemon that's running, that partition of that data disappears. Now, we have inbuilt replications, so there may be 2, 3, 4, 5 copies elsewhere on the other nodes. And so what happens when we introduce a node is we need to do a process of rebalancing that data across the nodes, and internally we call that migrations. And so what we're now doing is ensuring that as we go from 1 to 2 nodes, that we spread that data across those nodes. As we go from 2 to 3, we're now spreading that data across all 3 nodes. Because we're a hashing-based system, it means that essentially we're taking a random set of data to populate that third node. It's not like some of the other kind of range-based systems that people may be familiar with, where one node will get penalized as the data is moved. We're going to take bits of data across the whole cluster in order to formulate the data for that third node.
All right. Next question is it correct to think of Docker engines like Swarm 1, Swarm 2 as about separate VMs?
That's a good question. So, you know, you could think of this as two ways, which is Swarm 1 and Swarm 2 could be virtual machines, and essentially the containers within them are the processes that are running. But if you did that in a virtualization world, then those processes that are running will intermingle and interfere with each other, right? So the virtual machine, the better analogy is the container is the virtual machine, right? Because it gives you that process isolation. And then inside the Docker engine, you're running multiple of those. So it's like it's like kind of dealing with the virtualization master, so to speak, for those individual instances that are running.
All right. That brings up, I believe, our final question. In case, unless anyone else wants to submit a question right now, we have one more question, and that is, is anyone using Aerospike and Docker in production?
Great question. We have a couple of customers who are moving very rapidly to getting into production. As always, we get to work with some of the kind of, the leading lights of the industry. They've got real need to get to ensure that the deployment of all their software fits a standard model. They are standardizing on Docker. And so we're working very diligently with them to make that happen. And this comes back to the question we talked about earlier, which is we want to ensure that we have the correct sizing guides and the correct recommendations before we'd like to see people doing that en masse. And so we're working diligently towards that. And I suspect that a few months down the road, we'll be ready to actually publish all of the appropriate information so that the general public could do that. Right now we're working with a few specific customers so that we understand really what this means, not just in our sort of pseudo production environments in our lab, what it really means for real customers in real production.
All right. I believe that does it. Thank you very much, Alvin, for your time, and thank you very much, everyone, for attending to listen to this fascinating discussion of the future, basically the future of databases and deployment. So if you are looking for more information on this topic, the slides and the recording from this webinar will be sent to you, and as you can see here, there's plenty of contact information for you and email addresses. Once again, thank you all for attending. Thanks from me, Alex Handy at ST Times, and thank you from the folks at Aerospike. And I'm sure we'll have more information for you as time goes on. Thank you.
Thanks, everybody.